use some of my current research in collaboration with the Coastal Fluid Dynamics Laboratory at NCSU. And I hope that with my talk, I'm also able to convey what I think is very significant and relevant role of the statistics in the type of problems in geosciences that we have been discussing today, for uncertainty quantification, to bring together deterministic physical models with observations, and for stochastic parameterization of these deterministic models. But let me start with a little bit of motivation for the research that we are conducting here. So over the last 15 years or so, in the United States, along the coastline, there has been an enormous residential as well as commercial investment in these areas. And that has led to a very stressed ecosystem as well as a higher human and property exposure to storm hazards. So what we are trying to do is to understand the risk posed on the coastline to these hurricanes and tropical storms. So we are trying to forecast the storm surge. So this is the seawater elevation associated to these very strong winds caused by hurricanes. So we are trying to do very short-term forecasting as well as handcasting. The way it's being conducted right now is this purely based on deterministic models. So there is this model called the PAM model, the Princeton Ocean model, that is a series of differential equations for the conservation of mass, turbulence, heat, salt. And this model here, the PAM model has several inputs: the temperature, sea surface temperature, current, and wind fields. So here the wind fields are the forcing fields, the really important input here that affects very much the forecast that we do. So this is the type of framework that we have developed to be able to improve the storm surge. So there are two aspects of this framework that I want to emphasize. So one is blending together the deterministic model, the Princeton Ocean model, with observations that we have for the water elevation. So this aspect here of combining the deterministic models with observations. And the other important aspect is here to improve the inputs for this model, the forcing fields, which are these hurricane wind fields. So this is the focus of the presentation today, how to improve these forcing fields. So at the moment, the way it's being done is using another deterministic model, is the Holland model. But what we're trying to do here is also introduce other sorts of information, introducing information from data to improve the prediction of these forcing fields, with the focus of improving the final forecast. Is there a way to turn off? Yeah. Okay, thank you so much. Okay, so this is the Holland model. So this is the model that is being used to generate these forcing fields for the Princeton Ocean model. So this model has a series of parameters here: the hurricane central pressure, the ambient pressure, and all that is being obtained from the Hurricane Research Center. And there are two parameters: this B parameter, that is the shape of the pressure profile, and this R parameter, that is the radius of the maximum sustaining winds, and this is estimated from the data. Or in many cases, those parameters are also fixed based on historical data. So then once we obtain these double Qs at each location from these Holland models, we just obtain the U, the V component for the wind field. So this is symmetric model for the wind fields. So with this Holland model, we obtain the input, the forcing parameters for this storm surge model. But maybe let me show you a little bit how it looks like. So this is, on your left here, this is the Holland model. This is for Hurricane Charlie in 2004, Hurricane Category 4. And then this is the output of the ocean model that will simulate this water elevation, the storm surge. So as you can see here, so this is a symmetric model, very simplistic model. So the focus here is to be able to improve these forcing fields that will lead to an improvement in the forecast of the storm surge. But there are other sources of information about the hurricane wind fields that are not being used right now in the context of trying to improve the forcing field. So we have satellite data, and then we also have buoy data. And then we have the information from the National Hurricane Center that would give us which one is the storm surge center and the central pressure that we need for the Holland wind model. So just to show you a little bit how it could be of interest to make use of these other sources of information. So here what we have, this is for Hurricane Ivan in 2004, got to be Category 5, and this is in the Gulf of Mexico. So here we have the different sources of information for the wind field. So the first graph here, this is just satellite data, and you can see the asymmetries that we have for the wind fields, for these vectors. This is the buoy data. And then here we have the Holland model. And if you take the difference between the satellite data here and the Holland model, you can see that there's a lot of structure maybe still left to explain potential asymmetries in the winds. So the goal here is to be able to introduce a framework that would allow us to combine these different sources of information, the satellite data, the buoy data, with the physical knowledge of the hurricane surface wind fields, as well as characterizing the different sources of information that we have in the data and models, with the purpose of being able to improve the prediction of these forcing fields. But we want to make sure that this framework can be implemented in real time, so we need to balance the development of a very sophisticated, potentially very sophisticated statistical model that would be computationally and efficient. So we need to sort of balance a little bit the development of the methodology that would allow us to explain these complex spatial processes, they are the wind fields, but something that can be used in real time. So this is the type of statistical framework that we have developed to combine the different sources of information with the goal of being able to improve the wind fields. So we have the buoy data, we have the satellite data, and then we have the truth that we don't observe. So the truth is the underlying process of interest here for the wind field. So the buoy data would be the truth, but there is also some measurement error. Then we have the satellite data that also would have some random deviations with respect to the truth, and then some bias, some potential bias. And then the truth will be modeled as a function of this physical model, but with some error that will be explained by some stochastic components. So this is the diagram for the general framework that we're implementing here. So let me go into a little bit more detail about how we actually model each one of those. Really, regression models, this is really what it is. So, so we have here, this would be the observations from the buoys. So this is the buoy data. And then that's a function of the truth, so that's the truth plus some error. So the hat indicates the observation for the buoys. And then we have satellite data that will be the truth plus some error and some potential bias. So here, the bias, you can make it changing across space, changing across time. For the case here, the bias is not changing across space, and it's not changing across time also constantly. It's only changing every 3 hours when we get the satellite data updates. And then we have this underlying truth that could be just treated as a Holland model, and that's what is currently happening. So we just made it to be the Holland model, but we know that there is a lot of asymmetry structure that is left to explain by this simple model. So, so then we add some stochastic component that will help us to explain not only the asymmetries, but really complex behavior in the multivariate wind field process. So the challenge here is that some discussion that we previously already had here. So where do we put our effort? So we could really try to make this deterministic model more sophisticated, and there is obviously quite a lot of work that is being done on that. Along those lines, we have a version of the Holland model that is asymmetric, so we can introduce more and more parameters and make it more complex. So we will have the weather model, so that, we can put much more effort on this deterministic model, and then alternatively we could put more effort on the stochastic component. So I think that maybe a hybrid approach would be what is ideal here. We want something that is simple to run. We can run that in real time, and it works. So probably just focusing on one and trying to do all that in a deterministic form is maybe not the direction to go, at least right now in this road. We wouldn't have the computer power that we need to be able to run these deterministic weather models at a high resolution that we need when we work with hurricane wind fields. And the same thing, if it's all stochastic, it would have to be a very complicated stochastic model to be able to explain the complex structure of wind fields. So what we're trying to do here is a compromise. We are working with a relatively simple determinant, and the stochastic component, unfortunately, is not very easy to explain, but we're also introducing something that is very computationally efficient, but is flexible enough. And one of the aspects that we need to go beyond what is standard models and statistics for the stochastic component is going beyond stationary. So our model here is not non-stationary. So before I go into that, let me explain a little bit what I mean by stationarities. And in a spatial context, when we talk about a stationary, what that means is that the dependence between two locations as characterized by a covariance is just a function of the relative distances to locations of interest. So this is a vector distance. So that's what a stationary means, that our dependence is just a function of relative positions of the two locations of interest. So that means that the spatial dependence would be not a function of the location where you are. And then we define as isotropy a process when the dependence is just a function of the Euclidean distance, so direction does not matter. So that's the assumption of a stationary, and for the most part, with a lot of physical processes, might be realistic. No one will talk about winds. So we tend to work with parametric models that explain this type of stationary spatial dependence. So there are different models, exponential type of models, or mature models. So there are parametric models that would look like these. So exponential curve decaying with some parameters that could be estimated from the data. But let me show you what would happen if we work with the stationary models, the type of implications that it could have when we are working with wind fields. So this is with Hurricane Floyd in 1999, got to be, I think, Category 4. And here what we are doing is trying to predict the hurricane wind fields. And this is, I'm showing you here what happens to the V component, similarly to the U component. It's a particular location where we have a buoy, and we are trying to predict what the wind would be without, of course, using the information from that buoy. So, so in blue, what you have is dashed line here. This is what the Holland model would tell you, that the V component would be at a particular location across time during Hurricane Floyd. And then what we have in black, that would be the actual observation of a particular location. So you can see that the Holland model tends to, underestimate what the values of the wind would be. And this is what you would get in red, the dashed line in red, is what you get when you are using this hybrid approach that you combine the Holland model with the data. And they're a relatively simplistic stationary model that is just stationary. So we just add some stochastic stationary across time with one of these exponential standard models to explain the spatial dependence that we have. So that's what you get, this red line, and then we have here 95% prediction intervals to understand, the uncertainty that we have there. So under the assumption of the stationary, what the results are here on your right, And when we build a non-stationary model, you have the results here on the left. So you can see that it's not only that you get a prediction that is closer to the truth with a more realistic type of model that explains the spatial dependence, but also the coverage that you have. So here actually these are 95% prediction intervals, which means 95% of the time you should be there. It's actually about 40% of the time that you are there. So it's not just the actual estimation of these forcing wind fields, but also the type of assessment that we are making about the uncertainty in your estimated wind fields. So the bottom line is that we had to be careful in terms of using a very simplistic model for that stochastic component, because you can see the implications of going with something that is a little bit too simplistic, which is really the standard. This is what we call the, a Kriging approach with a stationary covariance. So what I'm going to try to do here is to introduce a non-stationary framework. But they tend to be those type of approaches for non-stationary. They tend to be very computationally expensive because you start putting a lot of pressure to explain that complex spatial dependence. So we're trying to do it in a still introducing a general, flexible, but not very computational framework to characterize really the complex spatial patterns that the hurricane wind fields would have. So that's what we're trying to do. I'm going even beyond the assumption of normality. So that's what we're trying to do here. And to be able to accommodate this really large variability across the space of the wind, we are introducing here what is called a nonparametric model, nonparametric spatial model. And the name for this type of framework is, this type of model is called the stick breaking. So I'm going to try to introduce this, this type of approach in the non-spatial setting, and then we'll move to the spatial one. So, so we are going to treat this, the distribution for this stochastic component that is going to help us to explain better what is the complex spatial behavior for the wind field. So that stochastic component has some distribution, and we have seen that if we assume a stationary and a Gaussian process, really don't do much. You know, it doesn't really help us enough to get accurate prediction of our forcing fields, which is critical to improve the storm surge forecast. So let's treat this distribution as something that we don't know, because we don't really know what is the distribution of this stochastic component that is left there. So, so we are treating that distribution as something that is unknown. So in a Bayesian statistical framework, what we're going to do is just put some type of prior vision for the actual unknown distribution of interest. So we treat it as unknown. And we have been modeling that with a mixture. So here the expression that we have for the unknown distribution is a mixture. So here is a mixture with some probabilities. So the distribution is taking some values, theta, with some probabilities. So this is the Dirac delta. So this distribution is taking some values, theta, with some probabilities. And this is called a stick breaking because all these probabilities add to 1. So I usually explain this with a stick. So if this was a stick, so this adds up to 1. So these are all the probabilities. So this is my stick. And what happens is that if we break the stick, so if we actually cut it, in this case, so this would be the first probability. So this would be P1. So this is the first probability of fraction of the total mass of the entire stick, which is 1. So this is P1, explains a fraction of the total, and this is the remainder. So this is the remainder of the stick after we accounted for probability P1. So what we do, we break the stick again, and this is the second probability. So this is P2 that explains a fraction of the remainder. And we keep doing that, so till there's not much left to explain, nothing to explain. So this will be P3, fraction of the remainder, and then at some point there is nothing left to explain. So that's why it's called a stick breaking, because we keep breaking the stick here. So the stick would be 1. In this case, the stick was 1 yard. So, so the different probabilities would add up to 1. So here you have the first probability that explains a fraction of the total, and then the subsequent probabilities that would explain some fraction of the remainder. So this product here is just the remainder. So this is the probability that's left to explain after accounting by the previous components, and this is the fraction that explains. So it's a relatively simple concept. So these are probabilities of taking different values. So you have the thetas, and then you associate to each one of those potential values a probability. So without being very technical, but just a few things to emphasize here. So these thetas would come from some known distributions and the Gaussian distributions. These probabilities, they are unknown between 0 and 1. Those is, so we treat them with a, we put a prior will be a beta distribution. And this mixture is truncated. At some point, there is not really much left to explain. It's negligible, so at that point we stop. So, so what we do is we treat here the wind fields, so the process of interest, as taking some values that come from one of these type of distributions, the stick breaking plus some error. So this is the negative effect. So this is the type of model that we adopt. So this would be a way to illustrate what we are doing here. So you take certain values, theta 1 with some probability P1, theta 2 with some probability P2. Okay. In terms of taking this to the spatial context, to introduce a non-parametric, no Gaussian type of model for the stochastic component that we have here left to explain. So what we do is that, okay, well, the wind fields are going to take certain values. Let's be in the univariate case. I know that we have the U and the V to worry about, but let's just think about the U component or the V component in this case. And you take certain values with different probabilities. So this is the theta, which would be the values that you take with different probabilities. So this index here for the thetas will tell you what is the probability associated to each one of those values. So to make this to change across the space, this is not a trivial thing. How to allow this to change across the space, characterizing the spatial dependence. So what we are proposing here to do is to put a kernel. So these probabilities, now they have to change across the space. The probability that you take a value of theta 1 for the wind field is a probability that changes across the space. So a natural way to make that probability changing across the space is just multiplying here the V's that we had before, the fraction of the total, by a kernel. So it's just like smoothing out the probabilities across the space. That's all that it is. Okay. So now this W is really a kernel function. So this is the way it would look like. So it's the same as before. So the unknown stochastic component now has a very flexible type of distribution. So it's this mixture that would take different values with different probabilities, and the probabilities change across the space. So it's going to induce very flexible type of spatial dependence that can be non-stationary and it can be non-Gaussian. So these probabilities, again, are the expression you have seen before with the kernel. So a simple kernel that we are using here is this uniform kernel that is a certain nodes here, each of the nodes, and this will be the bandwidth. So this is a simple uniform kernel that seems to perform very well in this setting. So just to illustrate with an example, a toy example, what we are doing here. So this is in the one-dimensional case here. So so this will be the different locations of interest. So here we are working between 0 and 1. And here what I have are the probabilities. So these dark black will be the probability, the first probability. So that we have the different P's that would explain, you know, like here, the different P's would explain a fraction of the total mass, that is 1. And at different locations, you have different probabilities dominating. So when you are here at 0.5, it seems that the P1 is the one that dominates. And when you are here going more to the edge, you have here probability P2 dominates, here probability P3 dominates. So those probabilities are associated to different values. So really, depending on where you are, the first component is the one is most likely to correspond to this particular location. So depending on where you are, you will have, as I said, different probabilities dominating. And this will be the type of spatial dependence that is being induced here, which is clearly non-stationary. So here what we have is this would be the spatial correlation. Well, in this case, is one dimension, so it would be temporal, or just one dimension. So these are the locations in our domain between 0 and 1, and you can see what will be the correlation between any location, let's say 0.4 and 0.6. So these will be the values of the correlation that you obtain from this model. And as you can tell here, it's non-stationary, because if it was stationary, you wouldn't have this type of ridges here, type of what is non-stationary behavior, because the dependence would be just purely a function between S, distance between S and S prime, and you wouldn't get this type of behavior here where you have more black, darker colors here when you are in the area of between 0.4 and 0.6. Yes, there's much stronger correlation that you will get just when you move a little bit more to the left or to the right. Okay, so this type of behavior could not be explained by a stationary process. So let me show you a few simulations before I move to the actual data to illustrate how it works. So here we're generating different surfaces. So this one is a surface with some trend. This is some waves here. This is very much a step function. This is sort of the way the wind fields will look like. And so we have these different surfaces, and we are going to fit this standard stationary Gaussian fitting approach compared to this stick-breaking spatial model that we are proposing here. So, so we compare the performance of a completely flat surface, no mean, no changing, nothing changes, versus the trend that surface that we have seen the first one, the waves, the steps, and what is sort of simulates the type of surface that you have for wind fields. And what we do that we generate those type of surfaces 10 different times, and we'll calculate the error. We compare the prediction that we get from the standard Gaussian stationary stochastic component with our spatial stick-breaking model using a uniform kernel, using other type of kernels here, square exponential. So, and then we calculate, so we are calculating here the root mean square error, which is the difference between what you are getting and the actual truth. And since we are doing that 10 times, we can get actually standard errors. So what is clear here is that you can reduce drastically the error in a significant way, because we have the standard errors. You can reduce it by 20%, 30% by going to this more flexible type of model. What is also important is that the point I was trying to make at the beginning is not just the prediction, but the type of coverage that we get in our prediction. So when we say that we have a 95% prediction interval, is that really a 95% prediction interval? So it's important that we study the coverage, and that's what we are doing here. So this is the coverage that you are getting. We are supposed to get a 95% coverage here, and as you can tell, if you use the standard Gaussian process with the stationary covariance, you are not getting that nominal coverage that is expected. So the coverage might be 89% coverage rather than 95, but we are able to achieve the proper coverage with this type of model. So the bottom line is that it is important if we are going to add a stochastic component. It just doesn't work if you just say I'm going to add a Gaussian process with some stationary covariance. We really need to put some thought into what type of stochastic component you are adding. But at the same time, it can get really very computationally expensive once you start going beyond stationary. So I think that this is a good compromise, a very flexible model that, as I said, is very easy to implement and is not computationally expensive because it doesn't have big covariances to work with. It's just these simple kernel functions. So let's go now to the winds, to the actual data, and implement this type of model. So, so here we are working with the hierarchical setting that I first introduced for the winds, and now this is the model for the stochastic component that is left after accounting by the Holland model. So, so what we are doing here, this the wind field, so here will be for stochastic component. We have the U and V components. So what we do, we treat that as a mixture. So we are taking certain values theta with certain probabilities. So the probabilities change across the space using the kernel functions that we already have seen. And now the thetas are two-dimensional thetas because we have the U and the V components. So we have a value for the U and a value for the V. So, so here for the thetas, the type of distribution that we assume a priori is a normal, a bivariate normal here. And then we are going to compare that with what would be the default, the multivariate of the spatial Gaussian stochastic component that we already have seen when we had only one component. So we have two components. Probably the standard statistical approach to explain that the stochastic component would be, let's treat that as a Gaussian process, the U and V, but it's multivariate, so it has some type of covariance. So that covariance could be of this form, and this would explain the, assuming that it's stationary in this case, dependence structure across a space. So the covariance would be a function of space, and then this sigma would explain the dependence between the wind components. So I'm not saying this is realistic. This would be probably the first model that you would try. And introducing something more sophisticated than this could be really computationally expensive. Apart from the fact that we don't really have a lot of models in a multivariate setting that would characterize non-stationarity. So we evaluate the performance of our model with this standard Gaussian multivariate model by comparing the prediction that we are doing at the buoys and at locations where we have buoys, satellite, the location at which we have satellites. So here what we are comparing is the actual satellite data with the actual buoy data for the U and the V components with what would be our replica of those observed components. So this is what is called expected mean square prediction error. And if we compare the Gaussian model, that will have expected mean square prediction error of 517. We get 3.46, which very consistently, so a significant reduction, about 40% of the error. And if you look at the residual, so this would be on the top using the Gaussian model. This is the square of the residuals, so that means that the actual value, you remove the estimated value for your U and your V component, U on the left, V on the right. And what you can see is that with the Gaussian model, you have dark values, which means large error, in particular in the center, around the center of the storm, where the winds are more, they change more rapidly. And that's not the case once we introduce our model. So it characterized what is the structure everywhere, in particular in areas where it's more difficult here, closer to the center of the storm. So this is our predicted U. This is the predicted V value. This is for Hurricane Ivan. And what you see here is what is the correlation that we get here between the U and the V component. So this is the actual distribution for that cross dependence that we have, and it seems to be negative. So that means that there is need to introduce models that will characterize that type of dependence that is left after accounting by the Holland model. And this is just the distribution for the bandwidth parameters in the kernel. And really, what that's telling you is that it's centered about 0.17, which means that the span of the kernels is about 17% of the domain that we have. We have a model that is well calibrated, so here we eliminated some locations and we try to predict what the value would be, and with 95% prediction intervals, and we do 95% of the time. We just are just right on target. So so we are not only improving the prediction of the wind fields, which is the focus, but it really leads to improve the storm surge forecast. So this is just the last graph. So this is Hurricane Charlie. So here I have also an animation, but I just might skip that. But here this is the locations where we have the water elevation. So we use these forcing fields for the wind fields, and we compare what will be the water elevation at the stations at which we have the water elevation, and that would be the black value. That would be the value of the water elevation at those locations after removing the tidal signal. And in blue, we have the current operational setting that will be using the Holland model for the forcing fields. And then in red, we have as input our predicted surface, combining the Holland models with the stochastic component, and it seems that we are able to reproduce better what the storm surge will be. Thank you.
between the models you compared, do you have a sense as to what was the key thing to getting things closer to right?
I think the non-stationarity is key because with Hurricane Floyd, the non-stationary model, that was a parametric model. So I don't think it's key that it's non-parametric. I think non-stationary seems to be the key, but those non-stationary models, they were much more computationally expensive to feed. I think it's hard to separate the non-normal versus non-stationary aspect, but I think the non-stationary seems to be more relevant here.